Have you ever really thought about the air hitting your car when you're driving down the highway? I mean, it's this invisible force, right? A totally chaotic dance of pressure and flow that car designers have spent decades and billions of dollars trying to perfect. You get it right, and you've got amazing fuel efficiency, great performance. But if you get it wrong, well, that's a hugely expensive mistake. See, the problem is, predicting that airflow is one of the most ridiculously complex computer problems out there. But what if you could take a process that takes days on a supercomputer and shrink it down to just a few seconds on a single chip?
All right, so here's the game plan for this explainer. First, we're going to tackle what we're calling the billion-cell problem. It's a big one. Then we'll see what happens when AI steps into the wind tunnel. We'll unpack the secret sauce, this anchor attention trick. After that, we'll look at the jaw-dropping results. And finally, we'll explore what this all means for the future of, well, designing pretty much everything.
So to really get why this new AI approach is such a massive breakthrough, you first have to understand the sheer scale of the mountain engineers have been trying to climb. For decades, car design has been locked in this battle with a true supercomputer's nightmare. For a long time, the main tool in the toolbox has been something called computational fluid dynamics, or CFD for short. The best way to think of it is as a virtual wind tunnel. Instead of building a clay model of a car and sticking it in a real wind tunnel, they build a digital one and use some of the most complex physics equations known to science to simulate how air flows around it. It's an incredible tool, for sure, but it's got a huge catch. And here is that catch. To make that virtual wind tunnel work, the computer has to chop up all the space around the digital car into this massive 3D grid. And for a really accurate, high-fidelity simulation, that grid can be made up of 150 million tiny little cells. I mean, just think about that number for a second. 150 million. And here's the real kicker. A supercomputer has to solve all those complex physics equations for every single one of those 150 million cells. This isn't something you can just run on your laptop overnight. No way. This process ties up huge, expensive supercomputer clusters for days just to test one tiny little design change. It's a massive, massive bottleneck on innovation. But what if you could just sidestep that whole bottleneck? Just bypass it completely? Well, this is where AI comes into the picture. And trust me, it is a total game changer. I mean, this slide really just says it all. Look at the showdown here. The old way, you're waiting for days, you need a supercomputer to do the math, and it's a whole complicated process. Now look at the new way with an AI model. You get your results in seconds, it runs on a single GPU, and it can work directly from the engineer's design file. This isn't just a small step forward. This is a whole different ballgame. So the magic behind this leap is a new AI model called AB-UPT. Now, instead of brute forcing the calculation for every single cell, this model has been trained on mountains of simulation data. It actually learns the underlying physics. It's like it develops an intuition for how air is supposed to behave, which lets it predict the final result almost instantly. So the big question is, how on earth does it handle that mind-boggling amount of data, 150 million points, without just completely crashing? Well, it turns out it uses a really, really clever shortcut. Think about it like this. Imagine you're an artist trying to paint a super detailed picture. You're not going to try to look at all 150 million pixels at the exact same time, right? That's impossible. Your brain would just melt. Instead, you'd focus on the key areas, you'd sketch out the big shapes, and then you'd go back and fill in the details. Well, the AI model faces pretty much the same problem. And the solution is this really cool method called anchor attention. So instead of trying to analyze all 150 million points at once, it first intelligently picks out a much smaller representative group of what it calls anchor points. Then, these anchors all talk to each other to figure out the big picture physics of what's going on. And once they've got that, they use that high-level understanding to instantly predict the airflow for all the millions of other points. It's just like sketching that outline before you paint in all the details. Now, this little trick is the absolute secret sauce. For the nerds out there, it reduces the computational complexity from quadratic down to linear. But what that actually means in simple terms is that the workload doesn't explode as you add more data. It just scales nice and predictably. And that's the key. That's what lets this incredibly powerful model run on a single graphics card instead of a whole warehouse full of supercomputers. Okay, so that's the theory. It sounds pretty amazing, right? But does it actually work in the real world? Let's take a look at the results when they put AB-UPT head-to-head with the old way. The results are, well, they're just staggering.
I mean, just look at this chart. That bar on the left, that's your traditional CFD simulation, days of waiting for a supercomputer. And that tiny little bar on the right, that's AB-UPT running on a single GPU, taking just seconds. It's not an improvement, it's a revolution in speed.
But okay, speed is totally useless if you're not accurate. And this is where it gets really crazy. AB-UPT doesn't just keep up with other cutting-edge AI models, it actually leads the pack. When they compared it, it consistently had the lowest error rate for predicting both the pressure on the car's surface and the speed of the air around it. So yeah, it's faster and it's more accurate.
Now let's talk about precision, because for a car engineer, the aerodynamic drag is absolutely everything. For that, AB-UPT scored an R-squared value of 0.963. Now you can think of R-squared as basically a percentage match to reality, where 1.0 would be a perfect prediction. Getting over 0.96 is just incredibly good.
And it did even better predicting the lift, which is what affects a car's stability when it's going really fast. It scored an amazing 0.975. You know, these aren't just pretty numbers for a research paper. This is the level of reliability you need to make real-world engineering decisions.
So what does this all add up to? What does it all mean? Well, it's way more than just a faster tool. This really represents a fundamental shift in how we're going to approach engineering design itself. Just think about the new doors this opens up. Engineers can now run a simulation straight from their 3D design files, completely skipping that painful, time-consuming meshing step. And the AI is built from the ground up to respect the laws of physics, which means you can trust the results a lot more. You're essentially creating an instant, super accurate digital twin of your design's aerodynamics whenever you want. So for example, the model enforces something with a very technical name, divergence-free vorticity. But the core idea is actually pretty simple. It just means that the little swirls of air the AI predicts, the vortices, have to behave according to real physics. They can't just magically pop into existence or vanish into thin air. It forces the simulation to be much more realistic. And this, right here, this is the ultimate takeaway. We are moving from a world where an engineer could maybe test, a dozen design ideas in a month, to a world where they can instantly and dynamically explore thousands of different versions in a single afternoon. The creative floodgates have just been blown wide open.
And it leaves us with this really fascinating question to think about. For so many decades, what we could design was limited by how fast our computers were. But what happens, not just for cars, but for airplanes, buildings, you name it? What happens when the power of a supercomputer is available instantly, on a single tiny chip? The possibilities? They're really, really exciting.